So the Nuclear Innovation Alliance comes up with a combination of policy analysis, technical analysis, and different publications that really helps move the conversation forward. So it's both coming up with the ideas, the think side, and then the do side of going out and working with different stakeholders to figure out how we can take those ideas, those proposals, those principles, and actually put them into practice. As we look at deployment of nuclear technology, state and federal policy, how are we talking about how these different incentives or different programs that we're going to have are going to affect the deployment timelines for nuclear energy? Deep decarbonization, really talking with different folks in a variety of communities about what role nuclear can play in helping us meet the clean energy goals.
Just because the facts are A, if the narrative is B and everyone believes the narrative, then B is what matters. But it's our job in our industry to speak up proudly, soberly, and to engage people in this dialogue. Those 2.5 billion people that are in energy poverty, they need us.
America cannot meet this threat alone.
If there is a single country,
of course, the world cannot meet it without America,
that is willing to
but we're going to need you, the next generation, to finish the
overhaul
job.
nuclear regulation,
We need scientists to design new
and
fuels.
focus on net public benefit
We need engineers to invent new technologies. We
over absurd levels of radiation
need
protection,
entrepreneurs to sell those
then
technologies.
we will march towards this.
We need workers to operate assembly lines that hum with high-tech, zero-carbon
We have
components.
unlimited prosperity for all humans.
We need diplomats and businessmen and women and Peace Corps volunteers to help developing nations skip past the dirty phase of development and transition to sustainable sources of energy. In other words, we need you.
Okay, welcome to another episode of the Fire to Fission podcast, where we talk about energy-dense fuels and how they can better human lives. So we're joined today by Patrick White, project manager with Nuclear Innovation Alliance. How you doing, Patrick?
Doing pretty well. How about yourself, Mark?
Excellent. Super excited to chat with you. Let's start from the beginning. Who are you? Where'd you go to school? How'd you get into nuclear?
Yeah, definitely. Started my career at Carnegie Mellon University, did a bachelor's and a master's in mechanical engineering there. Was really interested in nuclear technology, I think even in high school. So I was really looking for opportunities to kind of learn more about what nuclear could do. So while I was there, learned a lot about kind of the basics of heat transfer, nuclear energy, interned with Westinghouse, got to see what the commercial sector is like. And then after graduation, went and worked for an engineering consulting firm in Washington, D.C., NPR Associates, for about 3 years. So got to see the ins and the outs of the commercial nuclear industry, kind of do a lot of analysis, technical work on commercial nuclear power plants. Really had a good time there, but found myself asking the bigger picture questions around nuclear energy, what role it could play, and how do we address kind of the policy questions that I was seeing that were stopping us from using nuclear energy more broadly. So thought, hey, going back to grad school is a great way to dive into this topic. So I went to MIT in 2015, was there for a master's and a PhD in nuclear science and engineering. And while I was there, was really focused on licensing, regulation, policy, big picture questions around nuclear. I got to contribute to the 2018 Future of Nuclear Energy and a Carbon-Constrained World report that MIT released that kind of outlined what role nuclear could play. And then spent my PhD focusing on regulation and licensing of commercial fusion technology. So really just been in the nuts and bolts and the weeds of nuclear energy for a better part of the last 10 or 15 years. Joined Nuclear Innovation Alliance in 2021 as a project manager, and I lead our work there on regulatory modernization and really all things nuclear. So really excited about the technology and love talking both way in the weeds on the details about the nuclear energy, but then also the higher level policy conversations.
That's awesome, man. It's been a fun career. I thought you were younger than you are.
I hide it well.
Yeah, it's like I feel like this guy's like right out of school, but he speaks like he knows a lot of stuff. No, when were you at Westinghouse?
I was at Westinghouse. I interned there in 2010 and then co-op there 2010 into 2011.
Okay, gotcha. This move back to nuclear for the master's and PhD or nuclear engineering, what motivated that?
Yeah, so what really motivated that was the idea of trying to really get into what is nuclear energy and being able to explain it really from the first principles basis. I think nuclear is one of those technologies that people will like to talk about, but to actually kind of understand the fine details of and what the implications are can be really challenging. How do you explain a nuclear reactor from the kind of the quantum science all the way up to a functional power plant and being able to explain why each one of those levels matters? And so that was something that I was really interested in terms of really having that expertise and being able to go as deep as people want to help explain the topics and answer their questions. At a certain point, if someone has a question or a concern about radiation, it's one thing to be able to give the high level talking points about, oh, radiation safety. It's another one to say, okay, keep asking the next question. Let's go as far down as you want to really help try to answer your scientific questions, your curiosity, and then also potentially have the way to get at what the insights the person is really interested in. When someone asks a question, they might be interested in the information, but it's also trying to figure out what's really motivating that question and how can you address maybe the underlying concerns. And so in my mind, the master's and a PhD was really a way to kind of focus in on that and say, okay, I'm going to spend 6 years of my life doing nothing but learning. And hopefully that sets me up for an interesting career.
That's awesome. That's kind of altruistic, but also kind of selfish. I mean, there's a lot of people that love school and love learning, right? Like
exactly. It was 6 years to just spend nothing but like 60 hours a week, just thinking nothing about nuclear energy, no other distraction. So yeah, it was a great use of 6 years.
That's awesome. And then where'd you go after your PhD? Did you go straight to the Innovation Alliance or?
Yep. Okay. Yeah. Went straight from nuclear innovation went straight from MIT right to the Nuclear Innovation Alliance.
And so what is Nuclear Innovation Alliance, and tell us about the org?
Yeah, so Nuclear Innovation Alliance, as it says on the website, is a nonprofit think and do tank focused on creating the conditions for success for advanced nuclear energy as a climate solution. So it's a bit of a spiel, but I think it really kind of gets to the core idea that we're an organization that's funded primarily by private climate philanthropy organizations that's really interested in the role that advanced nuclear energy can play in helping us meet our climate goals. When we take a look out at the science, at the modeling about kind of clean energy more broadly, we say, hey, you might be able to do it with 100% renewables in some places, but oftentimes if you include nuclear or kind of other firm energy sources, it really increases the likelihood that you can get to deep decarbonization or complete decarbonization. It can increase the reliability, it can decrease the cost, it can essentially accelerate your transition to clean energy. It really has a lot of potential benefits. And so what we're really interested in is what are the potential barriers to deployment of advanced nuclear energy? And then what are the technical solutions? What are the policy solutions? Or maybe what is the education and stakeholder outreach that can help get us there faster? So the Nuclear Innovation Alliance comes up with a combination of policy analysis, technical analysis, and different publications that really helps move the conversation forward. So it's both coming up with the ideas, the think side, and then the do side of going out and working with different stakeholders to figure out how we can take those ideas, those proposals, those principles, and actually put them into practice. So we do a lot of work on regulatory modernization, how to make the Nuclear Regulatory Commission more efficient and more effective as we look at kind of deployment of nuclear technology, state and federal policy. How are we talking about how these different incentives or different programs that we're going to have are going to affect the deployment timelines for nuclear energy? Deep decarbonization, really talking with different folks in a variety of communities about what role nuclear can play in helping us meet the clean energy goals, remembering that it's not just going to be electricity. We're also going to have to think about industrial uses, transportation. There are a lot of other uses of energy that we're going to have to decarbonize and what role nuclear can play. And then finally, innovation and entrepreneurship. At the end of the day, it's not going to be the federal government funding the green transition 100%. We're really going to have to rely on private capital, private companies to come out here and make decisions. And so what are the questions that investors are going to have around nuclear energy? What's it going to take for them to put the hundreds of billions of dollars that we're going to need in for a clean energy transition into the marketplace? And so helping to answer their initial questions and then maybe bring their concerns or their questions forward to folks in the advanced reactor community that we work with to help say, hey, the technology you're developing is really cool, but here are the concerns that are really out there for people that are thinking about deploying this technology. So how do you make sure you incorporate those in? So work across the spectrum. It's a relatively small organization. I think there's about 7 of us, but we do kind of work in really every area.
You guys pump out a lot of content and do a lot of excellent work for having so few people.
Thanks. We keep busy, I'll say.
Yeah. They're actually a bunch of slave drivers over here.
I'd never say that. It's a fun organization. One of the things that actually brought me to NIA was really the flexibility and breadth of the work. I mean, I think while I've been there, I've worked on licensing of reactors under kind of the existing regulatory frameworks. I've helped draft up new ideas of how to create regulation for future advanced reactor systems. I've worked on high assay, low enriched uranium, lots of nuclear fuels, and I still get to dabble a little bit in fusion just based on my PhD work on that topic. So it's been a pretty wide breadth of topics to work on.
That's awesome. The board of directors or your funding, would you say predominantly comes from kind of like high net worth individuals that are looking for a philanthropy outlet and believe in the cause?
Yeah, so it's primarily coming from foundations, actually. So it's
Okay.
from organizations that have traditionally supported clean energy projects, clean energy programs, and they're looking at broadening out their scope of, hey, we're not just doing solar and wind projects. We want to think about the full slate of clean energy
Yeah.
technologies. So that's primarily our funding.
Gotcha. And does it just cover the US, or do you guys look outside of the US too?
We're focused primarily on the US right now, just because that's where we're seeing, I think, a lot of the action on advanced reactors. But we do some work with Canada and the UK. And then we're always keeping an eye out for kind of other projects internationally for how we can talk with folks and where we potentially have high impact. But I think when we take a look at the policy landscape, really we're going to see a lot of the advanced reactors maybe demonstrated and deployed in the US or Canada. And so it's trying to figure out how to support those in the near term and then set up the conditions for essentially wide scale deployment in the 2030s and beyond. So I've imagined that will be something that we really start to turn on as we start to think about export of nuclear technologies and what role it could play in other countries.
Yeah. Awesome. Well, let's dive into some of the technical stuff because I've got lots of questions. And you're super smart, as you said. PhD, 6 years just spent learning. So
yeah, let's go. Love to hear them.
So we're hearing a lot of buzz right now about HALEU development. And if you talk to people about TRISO fuel, they say, well, it's not qualified yet. But a bunch of the advanced reactor developers talk about how they're going to use it. I view these as risks and buzzwords. Why don't you kind of describe HALEU for us and describe TRISO specifically? Let's focus on the fuel first, and then we can divert from there.
Yeah, sounds great. It's always good to start at the center of the reactor and we'll work our way out. Yeah, so when it comes to nuclear fuel, one of the big things that we'll often talk about is what's called the uranium enrichment level. So if we take a look at uranium that's out there in the world, it's composed of different isotopes, different kind of forms of the element. The primary one is uranium-238. It makes up about 99.3% of uranium that we find on Earth. And then there's a second isotope, uranium-235, that makes up about 0.7%. And that uranium-235 is the isotope that we're really interested in when it comes to nuclear energy. It's a specific isotope of uranium that's really easy to fission or split and release energy. And so the question is, how can we design different nuclear reactors and different nuclear fuels to take advantage of this uranium-235? So there's some reactors that are designed to actually use a uranium that has uranium-235 at its natural level of enrichment, about that 0.7%. So the CANDU reactors, for example, the heavy water reactors that operate in Canada, were actually designed to use natural uranium. So they don't require any uranium enrichment. Then if we start to increase the enrichment, and this is done through a process called, surprisingly enough, uranium enrichment, it's a little tautological here. What you can do is you can increase that level of uranium-235 from 0.7% to higher levels. And as you start increasing it to higher levels, it enables you to use different kind of nuclear reactor technologies and different fuel designs. And a lot of this gets into the nuclear physics of how one of these reactors is actually designed. But essentially, certain combinations of fuel and coolant are going to require higher levels of enrichment. And so the question is, how do we balance out how high do we want to enrich that fuel versus what's the technology that we want to use to generate power? So the light water reactors, the pressurized water reactors and boiling water reactors that we use in the United States require enrichment to about 5% uranium-235. And that's commonly referred to as LEU, or low enriched uranium. So we've been enriching fuel in the United States to this level for decades, and it's really the basis for 20% of U.S. energy generation. It's a really well-established industry. It's billions of dollars go into it every year. It's a pretty stable commercial product. As we start talking about some of the advanced reactor technologies, some of these different fuels, like you mentioned, TRISO, some of these different coolants, and we start talking about high temperature gas reactors or sodium fast reactors, there's a whole kind of suite of technologies we can talk about later. Basically, due to the kind of design of these technologies, they require that uranium enrichment level to go a little bit higher. So instead of going to about 5% uranium-235, we need to go up to about 10, 15, or 20% uranium-235. And they call this level of enrichment HALEU, or high assay low enriched uranium, which is a kind of a really silly way to say high enriched, low enriched uranium. The reason that we have kind of this archaic term is that this 20% uranium-235 enrichment level has historically been the cutoff between what's considered high enriched uranium, or things that are going to require kind of additional safety and safeguards requirements, and low enriched uranium. Right. And so it's this idea of how can you come up to this 20% enrichment level and then use that for your nuclear fuels. One of the problems, or one of the challenges of getting HALEU, is that right now there just isn't infrastructure in the United States to produce this fuel. As I said earlier, you can imagine there's a massive industry for trying to produce low enriched uranium for the existing nuclear fleet. For this high enriched uranium, or this high assay low enriched uranium, there hasn't historically really been a market for this fuel. So the companies haven't had the incentive to build out the infrastructure and really build out the capacity to produce these fuels. It's technologically no different than the fuel that they use today. It's essentially just repeating the process of enrichment to get to higher and higher levels. So we have the technology, we have the know-how, we have the experience. We have to actually build out the new facilities. And so the challenge is right now, how do we essentially create the demand signal that companies should invest in new infrastructure when the advanced reactor developers that are potentially going to use the fuel can't secure their fuel ahead of time to produce their orders. So it's a little bit of a chicken and an egg problem. We can't have the demand until we have the supply, and we can't have the supply until we have the demand. And so that's one of the things that we're working through right now, specifically with the federal government's advanced reactor fuels program, that they're looking at really trying to create the way to essentially resolve some of these market inconsistencies and create the demand signals we need. So that's long story on HALEU. How it actually relates to the fuel form you were talking about, TRISO, is essentially how can we use these higher enriched fuels in new forms that potentially give us better operational characteristics or better safety. So when we talk about the fuel that's in the existing light water reactors today, it's essentially what's called a uranium ceramic. So you take small little amounts of uranium oxide, you form them into pellets, and you stick them in long metal tubes. And that's the actual fuel that we have inside of a nuclear reactor. It's a really well-engineered product. We understand it really, really well. Again, we've been operating with these fuels for decades. But one of the challenges of these fuels is that under kind of high temperature conditions inside of some of the reactors, the light water reactors that we have today, if the fuel isn't sufficiently cooled, the material, essentially the metal tubing that the fuel's in, this zirconium alloy tube, can start to degrade and release hydrogen gas through interactions between the water and the metal on the surface. And this hydrogen gas can represent a bit of a safety issue. This is what we saw actually at the Fukushima Daiichi site during the 2011 Fukushima nuclear accident, was that they weren't able to cool the fuels. The fuel started to overheat, had this essentially non-nuclear, it's just a chemical reaction between the outside of the fuel and the water, released hydrogen gas, and that's ultimately what caused the explosion in units 1, 2, and 3. And so there's this question of, okay, how could we rethink what the form of our fuel is to potentially get us something that operates at a higher temperature and might be able to retain radiation better? And so that's where this idea of TRISO comes into play. So TRISO fuels are tristructural isotropic fuels, and they're essentially little
fancy way of
poppy
saying
seeds.
BBs, right?
Exactly. Well, I tend to actually use poppy seeds because it's about the size of a poppy seed. It's a little poppy seed of uranium fuel that's then wrapped in layers of silicon carbide. And those layers of silicon carbide help to retain the radionuclides that are released during the fission process, and also act as a really high temperature barrier for operations. And so you take these tiny little poppy seeds of nuclear fuel, and they can either put them into what are called pebbles. So it basically looks like something about the size of a billiard ball or a ping pong ball, depending on your design, or into large blocks called prismatic blocks. And that essentially acts as the fuel form for your reactor. So instead of having little ceramic pellets and long metal tubes, we're now having billiard balls of nuclear fuel. And these are stable to much higher temperatures and are much more effective at retaining the radionuclides. So the idea is, even under a wide variety of different operating and accident conditions, you don't have to worry about the release of radiation. And so it supposedly will give you a much higher kind of operating temperature that lets you do really interesting things with industrial heat or higher efficiency electricity generation processes. And it potentially gives you a better safety case. And so these TRISO fuels end up becoming a really interesting kind of next step in thinking about deployment of nuclear technologies. And that's why I think you're seeing a lot of different advanced reactor developers in the space really start to say, okay, how can we try to use these TRISO fuels in our design and take advantage of some of the experience that we have with them? While we haven't really operated high temperature gas reactors or these kind of TRISO fueled reactors in the United States in any kind of large numbers, there is some experience around the world with the qualification and operation of these fuels. So the U.S. Department of Energy had a program in the early 2010s called NGNP, or Next Generation Nuclear Plant, where the Department of Energy helped fund research into these TRISO fuels and actually start to do a lot of this initial testing. And I think that's really laid the basis for different companies like X Energy, BWXT, Kairos Power, Radiant. We could go down the list, but all these companies have said, hey, this fuel form is really well established. We really like the operational and the safety characteristics. So let's figure out how to incorporate it into our design.
Yeah. One of the issues that I've heard of it with TRISO is it's a new fuel source, and so it's not as qualified, or that we don't quote unquote know as much about it, which seems silly to me, but I have heard that as a counterpoint. Do you agree with that, or is that legitimate?
Well, so I think it's something where you're looking at two different sets of operational bases. I think people will oftentimes compare it to light water reactor fuel, where we've been operating it for the better part of 70 years in 100 reactors. And so we have just thousands of reactor years of experience with these fuels.
More than 100, right? I mean, internationally, globally.
Oh,
right?
yeah, yeah. And
100
in
in the
just
US.
talking the US. Yeah, exactly. Yeah, probably, I think it's about 400 internationally. So we've got just a massive amount of experience with these fuels, and we understand to a very high degree exactly how they operate. I think some people will then look at TRISO fuels and go, hey, we don't have nearly as much experience. And they might get a little bit nervous about some of the uncertainties posed by it.
Which is pretty silly. Like,
I mean, it's a little bit silly, but I think in some ways
Yeah.
it's a little bit reasonable. They're trying to make sure that they understand, okay, how do we need to, what precautions do we maybe need to take with a fuel that we don't have as much experience with? And I think that's something
Sure.
that we'd see with TRISO fuels, is that initially you might operate them maybe a little less aggressively, a little bit more conservatively. And then as you gain experience with operation, with manufacturing, with disposal, then you would say, okay, we can now sharpen our pencil and really use these fuels to their fullest possible potential. I think that's maybe one of the good ways to address the conversation of saying, okay, this is something where, yeah, we don't have as much experience with it, but let's figure out a way that we can generate that experience and then really utilize these fuels to their maximum benefit.
Gotcha. That's a good segue. You mentioned the advanced reactor developers. There's a bunch of them out there, lots of teams. We like the microreactors the best. Are you familiar with all of them? Do you have a favorite? And maybe favorite isn't the right word, but most ready technology. You don't have to pick one, but
yeah,
why don't you just kind of give us an overview?
Very familiar with the microreactors. I think it's been really exciting to see those, I think, come into popular understanding or wider scale discussion probably in the last 5 or 6 years at this point. Much like trying to pick your favorite child, I will never say which one is necessarily my favorite. But I think it's really interesting.
You can't tell us which one's tallest and which one's best at baseball.
Which one's fastest. Yeah, so I think there are a lot of different companies out there that are pursuing commercialization. The one that I think is probably closest to deployment is probably going to be BWXT with their Project Pele. So this is a project that's being sponsored by the Department of Defense to really look at kind of the idea of a deployable microreactor for military applications. And so it's the U.S. Department of Defense. They're interested in going fast and figuring out whether or not this is going to really be viable to help support national defense applications. And so they partnered with a company, BWXT, that has a lot of experience in the design and development of the U.S. Naval Reactors Program. So they're leveraging a lot of kind of the technical and manufacturing expertise there, and then saying, okay, let's see if you can come up with kind of a novel project. And so they're actually currently slated to look at the deployment of their demonstration reactor by 2025 out of the Idaho National Lab. And so I think that's something where it's potentially that big kind of first step of, okay, microreactors aren't something that's a reactor on paper. We're actually seeing it deployed in the real world and operated. And I think my hope is that would help give a lot of credence to a lot of the other advanced reactor developers that are out there where, hey, this isn't a pie in the sky idea. This is a real thing that companies can build and can deploy. And then hopefully that starts to get us down that learning curve where we see the first one, we build some excitement, we get some momentum behind it, and then we can see the other developers looking at deploying their technology in the back half of the 2020s.
How are some of these microsystems different from the conventional gigawatt scale plants?
So the first really big difference that you'll have between kind of the microreactors and the gigawatt scale plant is obviously enough size. You're going from about 1,000 megawatts down to 1
They're
megawatt.
truly the SMRs, right? I mean,
They're
these should
truly
be
the
these should be the
most
small
modular.
micro or small modular reactors, right?
Yep, exactly. And while it might seem a little funny to say that size is really important, there are a bunch of other things kind of within nuclear design space that are implications related to the size. The first thing is just going to be the amount of radiological material that's potentially available on site. When you scale down the reactor by a factor of 1,000, you're also reducing the amount of radioactive material stored on site by a factor of 1,000. And that can have a huge impact in the way that you think about the potential safety case of your reactor. When we start talking about these really large reactors, if you start having releases of kind of a significant fraction of the radioactive material stored on site, well, you could potentially have a very large emergency planning zone or areas where you'd have to take mitigative actions. When you come down to these really small reactors, we're reducing by a factor of 1,000 the amount of stuff that can actually go wrong. And that can have a huge impact, I think, when you talk about the siting of these technologies, because it's something where you're no longer having to think about maybe a 5 or 10 mile emergency planning zone around a reactor. Even under a worst case accident, the consequences might not even extend past the building itself or maybe even the site boundaries. That has a huge impact on microreactors.
It's kind of like a car blowing up versus a refinery blowing up.
Exactly. The second thing that you can really start to think about is what are the potential impacts of the size on the reactor decay heat. And so this is one of the really big things that comes in with nuclear reactor design. The one big challenge in nuclear energy is that even when you turn the reactor off, it's still producing heat, because after you've split atoms, the radioactive fission products that are still present in the fuel are going to produce heat over time. And if you want to keep the reactor in a stable state, you have to be able to remove that decay heat even after you shut the reactor off. And so with really, really large reactors, that heat load can be significant. Even if you shut down to a couple percent of the reactor's full power operation, you might still have a core that's producing a couple megawatts of thermal heat in the hours and days after shutdown. And so that can have a lot of implications on the safety systems that you have to have and how you think about the design and operation of this facility. You have to have a lot of things going right and a lot of systems and personnel and components to make sure you keep the reactor in a safe state. We can do it, but it definitely increases the complexity of the system. With microreactors, because we're going down again by a factor of 1,000 in size, we're also going to be going down by a factor of 1,000 in the decay heat. And so now we're maybe going from something that's producing megawatts of heat to maybe kilowatts of heat, something that you can say, okay, this is more comparable to a lawnmower amount of heat that we have to remove. Yeah. And suddenly this opens up a huge range of different design options and different, really design and operational things that you can do to try to keep the reactor in a safe state. You no longer have to have these large pumps moving large amounts of water to try to keep the reactor cool. Maybe you could do it with natural air cooling, or maybe you could use technologies like heat pipes. Or in some cases, they talk about even having what are called inertially cooled reactors, where the reactor itself can essentially heat up, and it will heat up slowly and then slowly release that stored up thermal energy over time after the reactor shuts down. So maybe you don't need any active cooling systems at all. And so really it just says, okay, by changing the size, we've completely changed the siting and safety parameters of the reactor. And from there, it kind of opens up, okay, how do we want to think about the deployment of this nuclear technology? And what are different options, different use cases it can fit in? So then it opens up things like, okay, could we use different ways to cool the reactor, different ways to operate the reactor, different power cycles? And it helps you move away from this traditional paradigm of a large gigawatt class reactor that's just producing electricity at steady state and takes 10, 15 years to build, but it's going to operate for 80 years in a standard spot, to maybe something where you say, okay, this is something that could be deployed or transported if it needs to be. It's something that could produce electricity at a site for a couple of years. Maybe the deployment could only take a couple of months because you don't need all the civil structural work. And so I think that's kind of the big thing that you really see as you go from the gigawatt class to the microreactor class, is an opening up of this design space and an opening up of the options.
I love that. I want to highlight one point in that you said you can have a different coolant, meaning you don't need water. That's been a, we'll say, misconception, or, well, a standard in the past. If you want to build nuclear, you build it close to a river or close to an ocean where you've got lots of water so you can cool it. But with these smaller systems, that's not necessarily a requirement.
Exactly. And so one of the reasons that you really think about trying to remove the heat from nuclear power plants is a lot of it comes back down to these darn laws of thermodynamics, that at a certain point, you can get a certain amount of kind of electrical energy or work out of the thermal energy that you're getting out of the reactor. But the rest of it is ultimately waste heat. It's heat that you have to put back into the environment to complete the thermodynamic cycle. For anyone that's ever been through an engineering program, it's a horrible class you'll have to take, but everyone learns that there's no such thing.
It was like my favorite. It's not horrible. Come on,
okay. I TA'd it and taught it a number of times, but some people did not enjoy their time in thermodynamics. Glad to hear that you're the exception there, Mark.
Yeah, that's the study of energy and like how energy works. Like it's super cool.
That's fair. And I guess as someone that does energy professionally now, you got a strong love of it. Yeah. But one of the really big challenges is that when you're trying to remove with these gigawatt class plants, you're trying to remove maybe 2 gigawatts of thermal energy. Well, that's a lot of heat that you have to remove somehow. And historically, the way we had done it is we had taken essentially large amounts of water and used that to say, okay, we're going to take a large amount of water, increase the temperature by a small amount, and then put it right back into the environment. And that's how you essentially transfer the heat.
Right.
And that's really just a consequence of both the size of the reactor and the fact that you need to make sure that you're constantly removing this heat, or you're going to have a huge impact on your safety and operations. With the microreactors, and even with some of the SMRs, I'll say, even things up to the size of, let's say, NuScale at maybe 77 megawatt electric, they're starting to look at how can you use alternative methods to try to cool your reactors. So one of the things they'll talk about is direct air cooling, where instead of having it essentially using a body of water to remove that heat, the thought is, okay, can we design a heat exchanger or a heat transfer system where instead you'll have air come in, just ambient air come in, and maybe have the air increase from, let's say, 70 degrees Fahrenheit to 90 degrees Fahrenheit as it moves through. And you can think about the design of your system and the operation of your system to eliminate that need on bodies of water. Because I think that is a huge thing that we're going to see both in terms of siting options and in terms of potential environmental impacts. Water usage is going to become a bigger issue in the future, not a less important issue in the future. And so trying to think about how we can design systems that really integrate in with communities and environmental effects is going to be really critical. So I think that's a great thing to hit on. And it's, especially true for the microreactors.
Awesome. Let's pivot to licensing. You had mentioned that some of these systems have different safety cases and they should be easier or faster to license. Maybe you didn't say that, but that's what I think. Tell us a little bit about that. Do you agree? Do you think they should be faster to license? There's just less hazard there, like we said. And when people think about nuclear, the regulatory problems are always the biggest hurdle, or many people point to that for why you can't do it. So how's it going to be different?
Yeah, definitely. So I think the big question is really how do we change our paradigm for how do we assess safety of nuclear systems? I think when you talk about the Nuclear Regulatory Commission and nuclear regulation in the United States, it's really important to remember that it's the product of an evolutionary process. We started out with a regulator in the early 1950s, really at kind of the birth of the nuclear industry, that was saying, okay, we've got this novel technology. How do we assess the safety? And how do we have a regulator that grows in parallel with an industry that's still deciding what technology makes the most sense? And over time, as the industry coalesced around the idea of large light water reactor technology, so did the regulator. They created regulations and regulatory processes and frameworks that all aligned with the idea of how to support this utility scale, gigawatt class light water reactor technology. And so as a result, the regulation really became locked in and optimized for that. Now, however, as we're kind of seeing this wider growth of different reactor technologies, like we talked about, different reactor sizes, the regulator and applicants are sitting and looking at the rules on the books and going, these don't necessarily apply. And so they have a process in the United States called the exemption process that essentially allows the regulator to essentially come up with one-off decisions for an applicant that's coming through if something doesn't apply. So an applicant will sit down with the Nuclear Regulatory Commission and say, okay, let's take a look at the giant list of regulations and say, this applies, this doesn't apply, this is not even applicable. This kind of applies, but we can use a similar requirement instead. And they go through this process, essentially a one-by-one decision making. And that is going to be something that I think is going to be effective for the first of a kind reactors that we're seeing licensed right now. But it takes a lot of active work between the Nuclear Regulatory Commission and the applicants to try to get through that process. What we're really interested in is as you start thinking about nuclear technology more broadly and what the next generation of nuclear could look like, how do we create rules that are really designed and optimized for a much wider variety of nuclear technologies and enable the much more effective licensing? Again, and it goes back to the microreactor example we talked about earlier. If we're reducing the size of a reactor by a factor of 1,000, we're reducing the amount of radioactive material by a factor of 1,000. How can we think through what are the design requirements, what are the analysis requirements, and what are the operational requirements that are really needed to ensure safety? We probably don't need to have 5 reactor operators to watch a single 1 megawatt reactor, just because the hazard's not there, the complexity is not there, and some of the operational challenges aren't there. And so the question that we have to come up with, the question that we really have to answer is how do we come up with the right set of rules, the right set of requirements, and the right set of processes that really help us ensure that we have safe nuclear technology, but also that we can do so in an efficient way, and that essentially the burden of the regulation is commensurate with the risks posed by the technology. And that's one of the big things that we're looking at now with this idea of trying to create new regulatory frameworks for advanced reactors. How can we create something that's not necessarily designed for one technology, but instead can be modified, crafted, or adapted for whatever reactor you're trying to license?
Okay, so I agree.
Okay, I feel like I didn't necessarily answer your question, so let's hear the follow-up.
Well, no, I mean, we're reducing the size and the risk by a factor of 1,000. So the licensing process should be commensurate with that. Part 53 is something that the NRC has been working with, and there's been an act of Congress to say, hey, make this faster, make this better, and it's been their effort, but it's still 1,000 pages. Can we reduce that by a factor of 1,000 also and get it down to 1 or 2 pages of rules, and we call it good?
So I don't know if we get it down to 1 or 2 pages.
What are the mechanics behind that, Patrick? Tell me how this works. Yeah.
Tell you how this works. So this is, I think, a really interesting question of how do you want to think about regulatory predictability and regulatory flexibility and the different choices you have to make when you think about designing a regulation system for any type of safety regulator. When we take a look at the existing regulation today, it uses a combination of design requirements, analysis requirements, and program requirements to try to ensure that nuclear power plants are safe. And so if we take a look at the existing light water reactors, they have all 3 of these. And this combination gets us safety. When we start talking about advanced reactors, and we start talking about microreactors, it's the idea of, okay, what are the actual safety requirements that we need to regulate nuclear technology to? And then how can an applicant try to demonstrate compliance with those safety requirements? And so the Nuclear Energy Innovation and Modernization Act, NEMA, was the piece of legislation that you're alluding to that basically told the NRC, go forth and figure out the new regulations for advanced reactors. And so the Nuclear Regulatory Commission staff took a look at all the existing work that was out there, all the work that had historically been done on nuclear, and said, okay, if we need to have something that applies to every reactor technology, let's just get rid of those design-specific requirements. Instead, amp up the programmatic, essentially the programs that an operator needs to have to ensure safety, and the analysis requirements, how they're demonstrating safety. And so the idea is if they had more analysis requirements and more program requirements, they could still get that kind of predictability that if someone fulfills both of those, they can get a license from the Nuclear Regulatory Commission for any type of advanced reactor. The challenge that the Nuclear Innovation Alliance and some other stakeholders really feel is that it's starting to limit the different options that different advanced reactor developers have in terms of trying to demonstrate what the safety case of their technology is. If you say you have to do the exact same type of analysis for a 1,000 megawatt reactor and a 1 megawatt reactor, well, that's maybe not the most efficient way to get to a much more streamlined safety case. And so what we're looking at for things in like 10 CFR Part 53, and as we kind of work through this rulemaking process and public comments and engagement with different stakeholders in the NRC, it's trying to figure out how can we really bring this rule back down to what are the requirements that you need to fulfill to actually ensure safety without having too many additional onerous prescriptive requirements. The one caveat to everything I just said, though, is that as we strip this rule back to its bare minimum, we also start to introduce some uncertainty into the process. If I say you have to show me that your reactor is not going to expose members of the public to excessive amount of radiation, and that's all that it says, well, there's a lot of uncertainty in, okay, well, how are you going to show that? And to what degree do you need to show that? And what analysis methods are acceptable? And what programs you need to have? And one of the benefits of these kind of more prescriptive regulations or the things we have today is that all those things are very clear. So if you're an applicant and you want to go through this process, you know that if you check off the following boxes, you can have a reactor that will receive a license from the Nuclear Regulatory Commission. If we had a much more flexible process, well, it starts to introduce a bit of uncertainty. Are you sure that the things that you're proposing are going to meet the requirements of the Nuclear Regulatory Commission? And are the requirements of the Nuclear Regulatory Commission, or essentially are the requirements that they're using accurate or reasonable? And so it starts to introduce a little bit more of unpredictability into the process. And so it's this tension between predictability and flexibility that we have to balance out. And I think one of the things that we're really going to see, and I think the way that we can move forward on this, is really trying to work with applicants for their very first reactors and say, okay, the first reactor might be a little bit harder to license just because there is a lot of uncertainty, maybe how you're going to demonstrate the safety case and what approaches you're going to use. But the question is, once you get the first reactor built and operating and you can demonstrate the safety and you can really start to show how you're meeting the performance characteristics that we know you can meet, how can we start to make that licensing simpler for your third, fourth, fifth, sixth, 20th, or 100th reactor? And that's the thing that I think is really interesting.
10,000.
Exactly. Oh, see, I love the way you're thinking on that one, Mark.
Hey, come on, guys. We're going big.
We're going big, yeah. And I think that's the question that we'll really start to see with the Nuclear Regulatory Commission and nuclear regulation, is once we start to have these standardized designs, making sure that we're leveraging the lessons learned so we're not going through this onerous licensing process for a reactor that we built 10,000 times. And I think that's a really big thing that we'll be working with the Nuclear Regulatory Commission, is, okay, right now we need to be focused on trying to get the first 10 reactors licensed, because that's really going to give us the experience and the information about the operations. And then the question is, okay, once we're all agreed that this can be operated safely, how do we do wide-scale deployment?
You characterize that incredibly well.
Oh, thank you very much. I think about this a lot during my
You're
job.
so well spoken, Patrick. I love it. I feel like I learn something from you every time, and I feel less angry about any scenario after I talk to you. It's wonderful. I am curious on part 53, this prescriptive versus, let's say, risk informed. Help me out. What's the
so the idea is that
Yeah.
we're trying to get to a risk-informed, performance-based, technology-inclusive
Right.
regulatory framework. And that is compared to a prescriptive, deterministic, technology-specific regulatory framework. So I guess that's the two dichotomies. I'm happy to talk about each one of those. But
well, and so the point that I wanted to make or pose to you is oftentimes the amount of work that you perform will fill the time that you have to do it, right? Mm-hmm. So if you give yourself more time to do a project, then you'll just work the entire time, and that's how long you'll spend on it. And my perspective is the physics of nuclear are so good that we've allowed ourselves as a society to spend a lot of time on it, even though it's not been necessary. And so that's my concern, is that because of some of the ambiguity around the new rules and not really focusing on how can it be as simple as possible, how can we use the simplest analysis and the fastest timeline. How do we avoid that? How do we avoid overworking ourselves and doing work for work's sake?
Yeah, so I think the way that we do that is that it takes a lot of deliberate action by both applicants and by the regulator to say, okay, why are we actually here?
One of discipline. The things I think, start with why.
Exactly. Project discipline. A lot of the times we'll talk about what is the regulatory basis for what is being done. So one of the challenges that we got historically with nuclear regulation is that companies were so concerned about whether or not they would make it through the process and the amount of time that it would take, that they were willing to throw whatever it took at the wall to see what would stick and what would help get them through the licensing process. So if the regulator would ask any kind of question, okay, we'll throw another 100 or 200 pages of regulatory analysis at you, with the idea of, okay, we'll just essentially agree to everything and try to get through the process as quickly as possible. One of the challenges, however, of that is you start to get a lot of regulatory bloat at that point. You have a lot of analyses where every single comment, question, side remark is suddenly taken as, okay, we need to submit more things to the regulator to try to demonstrate that we're safe. As opposed to thinking back to, okay, why are we here? And how are we trying to show that our reactor technology is safe? And so I think you're starting to see that there's some advanced reactor developers that are starting to say, okay, how do we really show our reactor safety case makes sense, meets the regulatory requirements? And then how can we work with the regulator to say, nope, this is really all we need. We'll answer your questions. We'll show you everything you want to know. But at the end of the day, we're going to try to keep this as simple as possible. And while I hate naming names, I think this is something where I can really say Kairos Power is doing a fantastic job with this so far on their.
I was about to ask for an example. Yeah. Give us an example, Patrick.
Yep. Kairos Power with their Hermes test reactor has talked a lot about, or at least people have talked about them as having regulatory discipline. That if you take a look at the licensing materials that they submitted to the Nuclear Regulatory Commission for their Hermes test reactor, it's very concise. I think their preliminary safety analysis report for their test reactor is about 500 to 700 pages. And this compares with thousands or tens of thousands for some of the prior reacters. And it's something. I was
going to say 500 pages doesn't feel real concise to me, but.
See, and if I'm saying it's shorter than a Harry Potter book, I think it's something reasonable. I could actually,
there you go.
And it's kind of a weird thing to think about, but if I gave you a 500 page or 700 page book, you could keep that in your head. You could probably keep an idea of what the threads of the story were the entire time you're reading it. Versus if I gave you a 10,000 page book, maybe you got better memory than I do, but I might be losing it. Yeah.
Yeah. One more point on that is how long does it take to read 500 pages, right? Maybe 10 hours to 20 hours, right? And font size
I could read it in a couple of weeks as opposed to 10,000 pages. You're not reading that. And if you're reading it, you're not retaining it.
Right.
And so I think that's something that Kairos has really shown, and they've had a very successful licensing process so far. Again, knock on wood, don't want to jinx them as they're still working on their construction permit. But they've really shown discipline in trying to keep a simple safety case and showing how the reactor is going to work. and then working with the regulator to say, hey, we're showing you 500 pages, but we've done the 10,000 pages of analysis or more. And anything you want to see, we're happy to talk with you. We're happy to show you why it's safe, but let's try to keep you focused on what you need to do to ensure the reactor is safe. And I think it's this kind of discipline that we're hopefully going to see for some of the advanced reactors that really lets you kind of recognize the simplicity and the safety of these technologies. And so I think when we're talking with advanced reactor developers, and specifically the microreactor developers, it's really trying to say, okay, how are you demonstrating the safety case of your technology? What does the regulator need to see? And then what do you need to show the regulator? NIA recently did a report on licensing efficiency. And so we had a workshop with a bunch of different advanced reactor developers, folks from the NGOs, different nonprofits, public stakeholders. And we basically asked them, hey, what goes well for licensing and what goes poorly for licensing? And had a really open dialogue with them about where the processes have been and where the process could go in the future. And one of the really big things that came along was this idea of putting yourself in the shoes of the regulator when you're trying to develop your application. Try to make it as easy as possible for them to reach the safety determination that they need and recognize what is needed for a regulatory judgment. Simultaneously, however, if that's what the applicant's doing, we also talked a lot in the report about having discipline on the behalf of the regulator, making sure the regulator says, hey, we got a lot of really smart engineers, a lot of really smart staff. Let's not go down rabbit holes unless we need to. Yes, the way that this reactor technology is achieving its long-term cooling might be really cool. You might want to learn more about it. Do you need to know that to actually get your safety determination? Well, in this case, you might not. And so you can say, hey, that's a really fun thing. I might look into it later, but for the sake of licensing, let's go ahead and say this is approved and move forward. And so I think it really ends up being kind of that, making sure that all stakeholders are thinking about how to make the process more effective. And really, again, and this is going to be the hard part, I think, over the next few years, trying to maintain accountability on both sides. When applicants bring applications to the NRC, hey, if they're good, let's celebrate and say, hey, these are best practices. If they do things that aren't great, okay, those are lessons learned and we'll have to incorporate that. And then similarly with the regulator, when the regulator does things well and the reviews go really quickly, hey, that's great. Let's capture exactly how that happened and keep doing it. And when the process goes off the rails, say, okay, let's revisit this and try to figure out how we make this a single time.
I think that's one of the problems, though. The regulator has nobody holding them accountable, right? Like, there's no one cracking the whip to say, like, do it. I mean, Congress once every 6 years, 10 years might have a NEMA that comes out, but otherwise there's no one to hold them accountable. Am I right in thinking that, or am I off base?
So I think you're right historically that there hadn't necessarily been a lot of accountability, or that it did definitely come in waves. Some folks at the NRC talk about a near-death experience in the mid-90s where Congress nearly shut off the NRC's funding due to concerns around organizational culture and operations. But I think it's really going to take kind of accountability from all sides. It's going to have Congress really coming in and taking an active role, saying, hey, at the end of the day, the NRC works for the American people. Make sure that they are working for the American people. It's going to take applicants that are really saying, hey, when things start going off the rails, please let us know. Please raise your hand. Please say, hey, we're doing our best, but this is breaking down. We'd like to get some relief on this. And then it's also members of the public really, I think, stepping in saying, hey, we want this to be an efficient process. At a certain point, there is a term in the nuclear industry where the safest nuclear power plant is one that's never built. And while that might technically be true, the bigger thing that I'm interested I mean, no, you can't argue that the safest one is one that's never built. But I think
well, no, because then we build something else that kills more people. So
right, and that's where I was going with it, where I think it's that bigger picture, where the idea is if the goal of the regulator is to really maximize public welfare, public health, public safety, and environmental quality, hey, not building nuclear power plants means that we're not meeting our decarbonization goals, we're releasing more air emissions, we're having a much bigger societal impact. And so how can we make sure that we're really telling the regulator, yes, we want to think about a balancing act of how our energy technologies affect society, and not go for kind of a zero risk portfolio. And that's something where when public stakeholders come out and talk about it, that's something that the NRC listens to. If the only voice that they're hearing is members of the public saying radiation is the devil's energy and we therefore must never have it, well, that's not necessarily going to be accurate. But if we can start getting kind of a wider group of stakeholders that talk about the importance of nuclear, but then also simultaneously will advocate for things like making sure the public is protected, making sure that we have equity and justice when it comes to siting and power plants and regulatory decisions. Then this full suite of voices, I think, really pushes us forward on a more accountable way. And as hard as it is, You just got to stay involved in the process. There are a lot of meetings, a lot of proceedings, but
Yeah,
I mean, what is it? Decisions are made by those who show up. So trying to stay abreast of it is a really great way to help maintain accountability for your regulator.
absolutely. That's awesome. I love that perspective. It's a great conversation. Who are some of the ideal customers for these systems? The big gigawatt systems make sense, right? We're going to sell that power into the grid. There's maybe some other applications for heat and industrial uses. So who are you guys seeing that are interested in these?
Yeah, so I think beyond maybe the idea of kind of the smaller municipal co-op, the smaller communities that are looking at trying to get into nuclear and think maybe an SMR fits for them, I think we're going to see a lot of discussion around deep decarbonization of industrial processes and transportation. Right now, if we get to 100% clean electricity by 2035, congrats, we have only reduced our carbon emissions by 1/3. We still have a long way to go. And so there are a lot of applications that historically we maybe haven't talked about a really clean way to think of decarbonizing. You're not going to power a steel mill with solar panels necessarily. And so it's trying to think about how different types of energy can really help enable the cleanup of those energy sources. So I think maybe the first customers will probably be chemical facilities. So Dow Chemical has recently signed an agreement with X Energy to really say what role can nuclear play in its chemical production. And so I think we'll maybe see a build out of interest in those. And then I think as we start to see more and more kind of conversations shifting around clean industry and clean technologies, you'll start to see more and more customers say, okay, what role could things like nuclear or carrier fuels like hydrogen produced by nuclear can play in clean up our processes? So I think it's really going to be major industrial customers first. And then as you see more experience with the technology, you might see move down the technology adoption. Who's going to be the first adopters of a technology? And then when is it going to become mainstream when we can really demonstrate the fact that you can build these projects on time, on budget?
Great. So Patrick, from your perspective, if we wanted to build more nuclear tomorrow, what's the most important thing that we would chase? What would we do to accomplish that and move the rest of the industry forward?
Yeah. So I think the number one thing that we have to do is just project, like, and this is something that's really on the nuclear industry. It's project management and execution. At the end of the day, it's doing the hard things right, or even sometimes doing the easy things right is really, really critical. How are you managing your personnel? How are you managing construction? How are you managing supply chains? These aren't things that are unique to nuclear, but it's best practices that actually help you deliver a project on time, on budget, and historically haven't necessarily been a focus area for the nuclear industry. At the end of the day, no matter how good nuclear technology is, if every project is twice the schedule and 4 times the budget, nuclear might not have a role in the future. So I think that's the first big thing. I think the second big thing is really trying to make sure that we have the demand signals out there that say, yep, we are really serious about clean energy, and we're serious in a way that's going to include nuclear energy. It's one thing to talk about, oh yeah, we have a renewable portfolio standard. We want a certain amount of renewables on the grid. Completely support that. I think it's a great thing, but is the goal renewables or is the goal clean energy? And if it's clean energy, let's say that. And let's make sure that there are incentive programs out there, requirements programs out there that allow different energy users and different utilities to look at the full suite of technologies that are out there and say what makes sense. And so I think those are probably the two really big things right off the bat. I actually would tend to put regulatory reform a little bit lower on that list. Maybe it's just because I breathe it on a day-to-day basis, but I think that's something that'll kind of sort itself out, and it's things that we're making progress on. But it's ultimately, I want this to be something where it is a market pull for nuclear energy and not a market push. We want to have energy customers out there saying, yes, we want nuclear energy because this is what makes sense. And that's going to be, I think, through a combination of project performance and through incentives.
I mean, the physics support it, so we should get there. Yeah. Patrick, this has been great. Leave us on an optimistic note. Where's it all going?
I think it's a really exciting time in the next 5 years, really watching our first demonstration projects coming online. I think we're expecting to see Kairos Power in 2026. We're expecting the BWXT Project Pele 2025. There's talk about having a couple more kind of smaller reactors like Oklo or Ultra Safe Nuclear Corporation, USNC, in the 2026, 2027 timeframe. And then I think as we talk 2028, 2029, 2030, we're going to see the large demonstration plants coming online. GE Hitachi is looking at building 4 reactors up in Canada, their BWR X300 technology up at the Darlington site. They're looking at building one in Tennessee. We've got the X Energy project on the Gulf Coast, 2028 timeframe. Then we've got TerraPower with their sodium fast reactor out in Wyoming in 2030. And this is really going to be the vanguard. It's going to be the first major projects. And I think from there, people are going to look at it and say, yeah, this is real. And that's how we're really going to see the takeoff in nuclear technology into the 2030s.
Awesome. Patrick White, this has been fun. Thanks so much for your time.
Thanks so much, Mark. It's been a pleasure.